Okay, now we'll cover a bit about matrix inverses. So really where it starts is this type of arithmetic problem here. 3x equals 6, for example, something easy like that. So if you think about how we solve it, we could divide both sides by 3 and work it out. We'll get x equals 2. But this idea of dividing, we don't have that in matrices. So we have to really consider what we're doing here. Really what it is that we're multiplying 3 by its multiplicative inverse, like this, on both sides. Okay. And what we get here, 3 times its multiplicative inverse, is 1. And this is really what we're doing when we do this type of like canceling off. We're really writing 3 times its multiplicative inverse is the multiplicative identity, 1. Now that may seem overly pedantic, but it's important when we move on to matrices, because here we don't have this ability to divide by matrices. That simply doesn't exist. We don't have that in matrix algebra. So what we need to do is find somehow an inverse to this matrix, and then multiply both sides of this equation, and then we will isolate the variables on one side and have a vector of values on the other side. Okay, this is in complete analogy to what we do in arithmetic. Okay. So we need to find, I'll write it out here, we need to find some sort of A inverse so that when I multiply both sides by this, A inverse, and I'll write out these numbers here too, where I'm taking that coefficient matrix to be my A. This is my A. Okay, so I need to find some sort of A inverse to do this. Okay, so let's try to do that. This is how an inverse works. If I have a matrix A, I find its inverse, multiply them together, and it doesn't matter if I multiply it on the left or the right, I'm going to get the identity matrix back, okay? So this is one case where you're guaranteed commutativity of matrix multiplication. Okay, and this is what I meant on the previous slide, that if we have this type of expression here, where we have some matrix of coefficients times a matrix of variables equals a matrix of constants, we can find the inverse of A, perhaps, and multiply it on the left like this, and then we isolate our variables and our constants. Okay. Now, to find inverses of matrices, we could potentially set up a system of equations and involving the coefficients in the coefficient matrix, and then trying to work from that to find the inverse. But it turns out to be very complicated. So we're going to make an observation. So to solve a system like this, you remember what we did. We wrote the coefficient matrix like this, and then we augmented it with this constant matrix over here on the right. And then we row reduced and kept on going until we got the identity matrix over here. And if we do get that identity matrix, we don't always, but if we do, then over here would be our solution. Okay. So we're going to take that same approach in solving this equation. I want to find this inverse, kind of like I want to solve for this vector of unknowns. And to do it, I'll just kind of partition this over here. To do this, what I'm going to do is take my matrix from the problem, that matrix at the bottom left. I'm going to write down those coefficients. Then I'm going to augment it with the identity matrix, which is this on the right. So it's in complete analogy to what we did when we're solving those systems of equations. Okay, so once I'm here, now I can try to row reduce the stuff on the left and see see what I get on the right. So let me I'll take 2 minus row 1, and minus row 1 from the third row. And feel free to pay attention or to fast forward if you're already proficient with your row reduction. I do have to work this out so that we can see what we get as an answer. Okay, and so this would be 0, 0, minus 4. Okay, and now I'm row reducing, so I've got to do it on the right as well. I didn't touch the top row. The second one I subtracted twice the first row from. Like this. Okay. And now I'll multiply the second row by 1/2 and the third row by -1/4. Didn't do anything to the first row. Okay, and here I've got this. Oops, made a mistake here. It can be very tedious to do all this arithmetic. Okay, we're pretty close to being done here. So I can add 3 times the third row to the second row and then subtract 3 times the third row from the first row. And then we get, sure enough, the identity matrix. So that's going to be 1/4, 0, 3/4, minus 1/4, 1/2, minus 3/4, and 1/4, 0, minus 1/4. Okay, that was a little, again, tedious from the arithmetic, which is kind of the name of the game when you're doing any sort of this matrix arithmetic. And we end up with this matrix. Okay, and if you multiply this by this original matrix that we had, you should find that you do in fact get the identity matrix back. So I could take my 1, 0, 3, 2, 2, 0, 1, 0, minus 1, and I can multiply it by that inverse, what should be the inverse. And we want to check, we always want to check our work in math, so if we do claim that something is the inverse, you may as well just take that minute to actually check that it is the inverse. Make sure you didn't get anything incorrect. So I could do this multiplication. I got 1/4 plus 3/4, so that's 1. That second one is 0. And then I've got 3/4 minus 3/4, so 0. We're off to a good start. Some really quick multiplication here. 2/4 minus 1/4, so that's 0. And then 2 times 1/2, great. There's 0 as well. And then I've got 1/4 minus 1/4, 0. Again, 0 and 1. Great. So that turned out to be the inverse of that original matrix. Okay. So this is one method that we can use to find the inverses of a matrix. Now, we're not always guaranteed that you have an inverse for a matrix, but you can certainly try. Okay. Here's some practice examples. You can try it on your own. Try to find some inverses for these. Instantly, you'll notice that you do still have to attend to the dimensions of a matrix in order to find its inverse, its potential inverse. Okay. Another thing we can do with inverses is try to solve these equations, and I'll just demonstrate that quickly. So my original coefficient matrix here is this, okay, and so you could write out this entire equation like this, or a system of equations like this. And now I can find the inverse of this matrix, multiply on the left both sides of this, and that would isolate the xy. So let's try that. So if this is A, I'm going to do that same routine that I did on the previous page. I'm going to quickly, and it should go a little quicker than last time. -1, 1, 0, subtract twice the second, or the first row from the second. Okay. Multiply this by 1/3, and at the same time I'll actually add 1/3 of row 3 to row 2. Okay, so that's going to give me 1, 0, 0, 1. And I'll do this quick first. -2/3, oops. -2/3 and 1/3. Okay, and then I've got 1 plus minus 2/3 gives me 1/3, and then plus 1/3 of that is 1/3. Okay, and just want to double check quick. 1/3 plus that. Yeah, that looks about right. We can double check if it's the actual inverse, and we may as well do this while we're here. Multiply that matrix by the suspected inverse here. It would be nice if I made a mistake so we can see what it looks like, but I don't think I did. Okay, so if I add these, I get 1, I get 1/3 minus 1/3, 0, 2/3 minus 2/3, 0, then 2/3 plus 1/3 is 1. So that is indeed the inverse. Now what I'll do is I'll solve this problem by multiplying on the left by A inverse on both sides of the equation. Okay, and then when I do that, I get this. Two and 3. Okay. So I'm going to multiply this. I got 2/3 plus 1, so 5/3. And then minus 4/3 plus 1 is minus 1/3. Okay, so what this says, if I reinterpret this as a system of equations, I found my x and my y. Okay, and we could just quickly double check. Yeah, and that works out. So this is an alternative approach to solving systems of equations. We can use the matrix inverse in order to solve those systems. Okay, and of course, with anything that we've come up with algebraically, we have a bunch of properties that we can look at. And it's also possible that we don't have an inverse at all with a matrix. But if you think about it, if we do have an inverse, then we would be able to find the solution to a linear system. So that kind of gives you a hint of where inverses wouldn't exist, or when they wouldn't exist. Namely, when a system doesn't have a solution. So if that's the case, then we expect that there would be no inverse. And that's what we see here. You can see that row 2 is actually -3 times row 1. So these rows are not linearly independent. Okay, and if we think back in terms of if these came from a system of equations, then we would expect that that system does not have a solution. Okay, you see how those are connected? The inverse of a matrix and the solution to an underlying linear system. Okay, and I'll leave this for you. You can try this out. You remember there's different ways that we could have that different types of solutions that we would have in a 2x2 system. And so I list some things here that you might want to try out yourself. And again, also some practice here. All right, that's it for today.